Suppose we have this literal equation which is C is equal to 2 pi r. This is the formula for the circumference of the circle, where C is the circumference and r is the radius of the circle. In this literal formula, C can be computed if r is given. So therefore, C is a function of r. However, we could also transform this one into r is equal to C over 2 pi by applying the multiplication property of equality by dividing 2 pi on both sides. Now, in this case, in this one, r can be computed if circumference is given. So therefore, we could consider this one as r being a function of C. So from C is equal to 2 pi r, we transform this one. We reverse the relationship to r equals C over 2 pi. And reversing a function may produce another function. Now, if C is the original function, if C is equal to 2 pi r is the original function, then this transformation here, this reversing, is its inverse function. Okay. Now, before we discuss, which is our topic for today, the inverse function, before we discuss inverse functions, let's tackle first some important concepts to fully understand inverse functions. So take note of this. Take note of these mappings. This is our f, this is x, this is y, this is 1, 2, 3, 4, a, b, c, d. 1 is mapped to a, 2 is mapped to b, 3 is mapped to c, and 4 is mapped to d. Then let's have another mapping here. Say this is g, 1, 2, 3, 4, a, b, c, d, e. This is x, this is y. 1 is mapped to a, 2 is mapped to b, 3 is mapped to c, 4 is mapped to d. Then we have h, x, y, 1, 2, 3, 4, a, b, c, d. 1 is mapped to a, 2 is mapped to a, 3 is mapped to c, and 4 is mapped to c. So consider these mappings, the mappings f, g, and h. For f, as you can see, 1 is mapped to a, 2 is mapped to b, 3 is mapped to c, and 4 is mapped to d. So we know that this one here is a function, and every element in x is mapped to every element in y, and exactly one element in y. So this is a function, and as you can see, the mapping is 1 to 1, meaning one element is mapped to one element in the other. So that's a function. So the mapping here is 1 to 1. For the g, this is also a function because every element in x is mapped to element in y, and the mapping is unique. So this is still a function. Okay, this is still a function. Now, for h, every element is mapped to element in y, and then the mapping is unique. However, 1 is mapped to a, and 2 is also mapped to a. This is still a function, but the mapping is many to 1. Although the function g looks like a 1-to-1, this is not considered 1-to-1 though. Why? Because there is one element in y which has no mapping from x. Now, let's take the reverse mapping of these three functions. So let's have the reverse like this. This is just notation of the reverse mapping. So we have here this is our y, this is our x, and this is A, B, C, D, 1, 2, 3, 4. This is A, B, C, D, E, 1, 2, 3, 4. This is A, B, C, D, 1, 2, 3, 4. For the first mapping, we have A is mapped to 1, B is mapped to 2, C is mapped to 3, and D is mapped to 4. Here, A is mapped to 1, B is mapped to 2, C is mapped to 3, D is mapped to 4, but E has no mapping, okay? Has no association in X. Now, for the third one, which is H, A is mapped to 1, A is mapped to 1, also A is mapped to 2. Then, C is mapped to 3, then then C is also mapped to 4. That's the mapping. So for the first mapping, for the first reverse mapping, this is also a function, because all elements in the first set is mapped to elements in the second set, and the mapping is unique. Now for the second mapping, the second reverse mapping, not all elements are mapped to the, not all elements in the first set, in the y set, is mapped to the elements in the second set, which is the x set. E here is not mapped to any element in x, so therefore this one is not a function. For the third one, A, which is the first element in y, is mapped to 1. At the same time, it is also mapped to 2, and the mapping is not unique. So therefore, this is not a function. So what can we say about this mapping? Reverse mapping of G and the reverse mapping of H are not functions, but the reverse mapping of F is a function. So therefore, another function emerges, which is an inverse of the original function if the original function is 1-to-1. In this case, this is 1-to-1, and another function emerges because that function is 1-to-1. However, these two mappings here, although they are also functions, but they are not 1-to-1. Therefore, the reverse of that are not functions. So for the reverse to be a function, the original function must be 1-to-1. So that's very important concept in dealing with inverse function. So what are 1-to-1 functions? This is the definition of a 1-to-1 function. A function f is 1-to-1 if no two ordered pairs in the function have the same second component and different first component. Okay? Remember the definition of a function in ordered pair. No two ordered pairs in the function that have the same first component and different second component. In this case, the 1-to-1, no two ordered pairs have the same second component and different first component. So example, if we have T, which is set of ordered pairs 0, 3, 0, 5, 4, 9. This one here, this is not a function. Okay? this is not a function. Why? Because 0 is mapped to 3 and 0 is also mapped to 5. Suppose we have another set M, which is a map of ordered pairs 0, 3, 2, 3, and 4, 9. This is a function but not one-to-one. Why? Because 0 is mapped to 3 and 2 is also mapped to 3. Okay, this is many to 1. Now let's have another set of ordered pairs, which is 0, 3, 2, 5, 4, 9. This one here is a function, at the same time is also a one-to-one function. 0 is mapped to 3, 2 is mapped to 5, and 4 is mapped to 1. So now, based from this definition, based from this concept of a one-to-one function, how do we determine whether a function is one-to-one or not? Now, to show if a function is one-to-one or not, we'll just have assume for a, b element of real numbers, we assume that f of a is equal to f of b, and we have to show that a is equal to b. Okay, this is our assumption. And this is our conclusion. Now, if we could do that for a, b element of R, then the given function is one-to-one. Okay. Example, if we have a is f of x is equal to 2x plus 1, and our b is f of x is equal to x squared. The first one is a linear function, and we know that this is a function. Then the second one is a quadratic function. Also, quadratic functions are also functions. Now, how do we show that this is one-to-one? So for the first one, we let f of a is equal to f of b. So therefore, 2a plus 1 is equal to 2b plus 1. This is just evaluating functions. Then, by applying addition property of equality, this is 2a is equal to 2b, meaning subtracting negative 1 on both sides. Then, dividing 2 on both sides, we have a is equal to b. So, by assuming that f of a is equal to f of b, we've come up with a is equal to b. So therefore, f is one-to-one. Now for the second one, let f of a is equal to f of b. Then a squared is equal to b squared. Then therefore, a is equal to plus minus b squared, or a is equal to plus minus b. Also, plus minus a is equal to b. So in this case, a is equal to b, or a is equal to negative b. Also, negative a is equal to b, then a is equal to b. So it's not unique. Okay, like a is equal to b. So therefore, the second one here, f is not one-to-one. So what is the importance of a one-to-one function to inverse function? Note that if f of a is equal to b for at least one pair of domain values a and b, and a is not equal to b, then f is not one-to-one for at least. Okay, so meaning it will give two or more pairs of A and B. So therefore, that is not 1-to-1. The example for that is our f of x is equal to x squared. A and B are not equal, and we have given two pairs, which is A equals B and A equals negative B, or negative A equals B and A equals B. So that is obviously not 1-to-1, because at least one pair of domain values A and B are shown for f of A is equal to f of B. Also, if the assumption f of A is equal to f of B always implies the domain values A and B are equal, then f is 1-to-1. So the example for that is our f of x equals to x plus 1. Okay, by assuming f of A is equal to f of B, we came up with A equals B, and that would happen always on the linear functions. So these are important notes in dealing with 1-to-1 functions. Now, if the graph of the functions are given, then it would be easier to identify if a function is 1-to-1 or not by using the horizontal line test. So a function f is 1-to-1 if each horizontal line intersects the graph of the function in at most one point, meaning at exactly one point. So if, for example, the f of x is equal to 2x plus 1, how do we graph that one? The y-intercept is 1. Then the slope is 2. 1, 2, run is 1. So this is the graph of that function. This is the graph of that function. F of x is equal to 2x plus 1. Now, if you draw a horizontal line and each line intersects at exactly one point in the graph, then that function, that graph of the function or that function is 1-to-1. So let's try to have this one. Okay, that line intersects at exactly one point in the graph. Regardless how many lines you make, then it only intersects at exactly one point in the graph. So therefore, by just looking at the graph, f of x is equal to 2x plus 1 is a 1-to-1 function. How about the second example? F of x squared, the graph of that is like this from our previous lesson. So this is f of x is equal to x squared. Now, if we draw a line, a horizontal line there, we know that from the looks of it, it intersects at 2 points in the graph. So therefore, it makes it not 1-to-1. Okay? So if we have another graph, say like this one, clearly this is not 1-to-1, because if you draw a horizontal line here, it intersects here, here, and here. So this is not a function. So that's the value of horizontal line test in determining whether a function is 1-to-1 or not. Let's have another note here. So if a function f is increasing throughout its domain or decreasing throughout its domain, then f is a 1-to-1 function. So if we have, say, like this, it is increasing throughout its domain, then that f is a function. Now, if we also have something like this, it is decreasing throughout its domain, then that function is also 1-to-1. However, if there is one part in the domain, one interval in the domain, that the function is neither increasing nor decreasing, meaning it's constant in that part, then that function is not 1-to-1. For example, if we have it increases here, then suddenly it became constant here, then became constant here, then increases again. Okay, so in this case, if we apply the horizontal line test here, then it touches at infinitely many points there, so therefore this is not a one-to-one function. Second note, so if there is a subinterval in the domain of f that is constant, then f is not one-to-one. Example in this one, there is a subinterval in the domain that makes it constant, and it makes it not one-to-one function. So we are now ready to define inverse function. Now this is the definition of the inverse function. If f is a one-to-one function, then the inverse of f, denoted by this symbol, is the function formed by reversing the ordered pairs in f. Again, this symbol here is not f to the -1. Okay, the -1 is not an exponent. This is just a notation for the inverse function. So the assumption again is f must be one-to-one for the inverse function to exist. Okay, so again, what does it say? Formed by reversing the ordered pairs in f. Okay, so the inverse function is the set of ordered pair yx if xy is in f. So it's just reversing the elements in the ordered pair. Also, as support for this definition, if f is not one-to-one, then the inverse function does not exist. So these are the properties of inverse function. If the inverse function exists, then f or the inverse is a one-to-one function. Clearly, it is a one-to-one function because if you take the inverse of the inverse function, we have to go back. Okay, we must have the original function. So it must be a one-to-one function for it to have an inverse, which is the original function. So the original function and its inverse are inverse of each other. Okay, inverses of each other. Then the domain of the inverse function is equivalent to the range of inverse function, and the range of inverse function is equivalent to the domain of f. Clearly, based from the definition, okay, we just reversed the elements in the ordered pairs, so therefore the domain of this inverse function is the range of the original function. So as the range of the inverse function must be the domain of the original function. So given an original function, how do we find the inverse of it? Suppose we have our function a while ago, f of x is equal to 2x plus 1. How do we find the inverse of x? So we follow certain steps as our guide in finding the inverse of a function. Step 1. Okay, take note of these steps. So determine first if the given function is a one-to-one function. So here we just show a while ago that f of x is equal to 2x plus 1 is a one-to-one function. Step 2, let y is equal to f of x. Therefore, if y is equal to f of x, we can write this one as y is equal to 2x plus 1. So we just substituted y to f of x. Then step 3, solve for x in terms of y. So here, from y is equal to 2x plus 1, this is equivalent to y minus 1 equals 2x, then divided by 2 on both sides. We have y minus 1 over 2 equals x. Okay, so we already have solved x in terms of y. Then step 4, interchange x and y. So therefore from here, we have x minus 1 over 2 equals x. So we just have interchange x and y. Step 5, change y to the inverse function notation. So from here, we have x minus 1 over 2 equals this one. Or we can write this one in a proper form, which is x minus 1 over 2. So this is now the inverse of the given function, which is f of x is equal to 2x plus 1. Okay, this is now the inverse function. If you try to find the domain and the range of these functions, you would know that the domain of f is the range of the inverse function, and the range of f is the domain of the inverse function. But in this case, since these are linear, the range and the domains are just real numbers. Let's have another example. So find the inverse function for f of x equals square root of x plus 3. Solution. Our step 1, check if it's 1 to 1. So let f of a is equal to f of b. Then square root of a plus 3 is equal to square root of b plus 3. Then applying square root property, we have a plus 3 is equal to b plus 3. Applying the addition property of equality, meaning adding negative 3 on both sides, we have a equals b. So therefore, this is a 1-to-1 function. Step 2, let y is equal to f of x. So therefore, our f of x equals square root of x plus 3 becomes y is equal to square root of x plus 3. Then step 3, solve for x. So we have from y is equal to square root of x plus 3. This implies that y squared by squaring both sides equals x plus 3. Then we have y squared minus 3 equals x. Then step 4, interchange x and y. We have x squared minus 3 equals y. Then step 5, we change y into the inverse function symbol. We have x squared minus 3 equals f of x, or we have is equal to x squared minus 3. So this is now our inverse functions. Now take note of this relationship between f and its inverse. So this is the relationship between f and its inverse. So if the inverse function exists, then x is equal to the inverse of y. If and only if y is equal to f of x, then this one, f of x, the inverse of f of x is just equal to x. So if we expand this one, what is f of x? Remember, we have f of x is equal to 2x plus 1 from our example. Okay, so that is inverse of 2x plus 1. And what is our 2x plus 1? That is our y. And from here, our inverse of y is x. So That's just what does. So that's what it means by f inverse of f of x is equal to x. That's for all x in the domain of f. So same argument with this one, the third one. F of the inverse of y is y for all y in the domain of the inverse. Now if it's interchanged, this is the relationship. Take note also that the graphs of y equals f of x and y equals inverse of f of x are symmetric with respect to the line y equals x. So let's have an example here. Okay, so again, our f of x is equal to 2x plus 1. What is the graph of that again? This is the y-intercept, then slope. So this point here, we connect this point here. This is our f of x equals 2x plus 1. And what is the inverse again? The inverse of this, that's x minus 1 over 2. So this is x over 2 minus 1 half. Let's use another color for it. Let's have yellow. So the y-intercept is negative 1 half. Negative 1 half. So this is 1. This is negative 1 half here. And then rise is 1. Run is 2. You have 1, 2 here. So we connect these points here. Okay, so this one here is the inverse function, which is x minus 1 over 2. As you can see, this is symmetric. So assuming that my graph is good, this must be symmetric in this line. This line here is y is equal to x. Okay. So these two lines must be symmetric on y equals x, assuming that my drawing is good, is okay. If you graph that one in the graphing paper or with the right measurement, then you can see that these two are symmetric through the line y equals x. So these are our practice problems. So try to solve this on your own.